All right, today we are going to make an apple pie. Yum! Ingredients you need for this apple pie are 3 apples, and you need a piece of pastry. This is pastry, by the way. Maybe there's, I don't know how to draw this better. All right, so once you've got your 3 apples and you've got 1 sheet of pastry, you land up with 1 apple pie. Yum! All right, but let's pretend that you actually got 6 apples today. I'm drawing the 6 apples. Aren't they cute? Do you like them? They kind of look like circles with flags. But if I said, okay, you got 6 apples today, how many apple pies can you make? That's right. If you've got 6 of them here, that's double the amount of what you had before. So that means you can make double the amount of apple pies. And that means, of course, you would need 2 sheets of pastry. This is pastry sheets. All right, so let's pretend now that we wanted to make half an apple pie. Well, if we wanted half an apple pie, that means we have to divide all of the quantities in the first equation by 2. So 1 divided by 2 means we get half an apple pie. We would land up with 1½ apples. So here's 1 and here's half the apple. And we will also have 1/2 of a pastry sheet. So you might be wondering, what does apple pies have to do with chemistry? Well, we are going to be learning about a new area of chemistry called stoichiometry. And it's pretty much what we've been doing with our apple pie. It's about using chemical equations, or in this case, an equation to make an apple pie, to figure out the amounts of chemicals that you need. So aka using a written up equation to figure out the amounts of chemicals that you need. So how about we actually talk about some chemicals? Before we do get into the stoichiometry part, we need to know how to write some balanced equations, and we've been working a lot on this throughout the year. So first of all, write a word equation, write a skeleton equation, and then balance the equation, remembering states. So let's have a look at the first one. The first one here is sodium hydroxide, NaOH, reacts with sulfuric acid, H2SO4, to produce sodium sulfate. Now remember, the sulfate ion has a 2- charge, so after swapping and dropping, it's Na2SO4 plus water. Alright, so we've got the worded, we've got a skeleton. Now we should start balancing. So let's see, we've got an Na on the left, 2 on the right. Oops, means we're going to have to double this up here. And then we've got 2 oxygens. Oh no, we don't. We only have 1 oxygen, so we're going to have to double that up. So now we need 4 hydrogens. So we've got 2 here, and we've got 2 here. Perfecto. And we have SO4, SO4. Balanced. Last thing we need is states. Sodium hydroxide in this case is going to be aqueous. Sulfuric acid, aqueous. Sodium sulfate will be aqueous, and H2O is liquid. So if I was to say, oh, you have, we're just going to go with these numbers in the front for now. These represent moles, remember. So if I said, oh, you have 2 moles of NaOH, how many moles of Na2SO4 would you get in this reaction? You'd say, oh, 1. Now, for example, if we had 4 moles of NaOH, how much would you get of Na2SO4? You would get double. So you would use that ratio to figure out the amounts of chemicals you have in other parts of the equation. All right, let's try the next one. Magnesium powder reacts violently with iron oxide to produce liquid iron and magnesium oxide. All right, magnesium powder means magnesium is going to be a solid. It reacts violently with iron 3 oxide. So remember, the charge on oxygen is -2, oxygen ion is -2, and the charge on an iron iron, which is 3, will be 3. So Fe2O3. We are going to have liquid iron, just plain, and magnesium oxide. Ooh, it's a pretty exciting reaction. Bit dangerous. All right. So let's see if we can balance everything at this point. Mg, is there an Mg on the other side? Yes. Fe2. Ooh, we only have one Fe on the other side, so we're going to put a 2 there. But hold up, we got 3 oxygens, so that means we need 3 over here. So we're going back to the magnesium and we're going to make sure we have 3 of that. Done. Let's put some states in. Magnesium powder, as I said, is a solid. Iron oxide. Well, in this case, iron oxide is a solid. It would be cool if we saw a video of the prac. Maybe I'll look for that. Fe is liquid and magnesium oxide is going to be a solid. Done. So, for example, if we had 2 moles of Fe2O3, that means everything on the other side would get doubled. We would have 4 moles of Fe, we would have 6 MgO. Likewise, if we had 1 mole of Fe produced, that means you'd divide everything by 2. So you'd have half Fe2, just like our apple pie. And we can do calculations and look at things from that perspective as well. So hopefully you're getting the idea. But I'll show you more of those. The main aim for the start of today is just to be able to write balanced equations. So we can't get very far on this topic without it. When solutions of calcium chloride and silver nitrate are mixed, a precipitate of silver chloride is produced. Beautiful. So we've got most of it, but we've forgotten the product that's going to be produced. So make sure you've got a balanced equation. Check if everything works on the left and the right. One thing here. Calcium's got a 2+ charge. So don't forget to put those little 2's there. Oopsies. Oh my gosh, I dropped my pen. All right, so first thing we got to keep a tab on is we are going to have 2 AgCl to make up for the 2 Cl's on the left. And that means we need 2 AgNO3. Voila, everything is balanced. Now, precipitate reactions we know are aqueous. Aqueous, a precipitate is a solid. And everything else is aqueous. Lucky last, propane burns in a barbecue. We know propane. Propane is that one with 3 hydrogens. Oh, sorry, 3 carbons. And here comes the little hydrogens. So C3H8. And when something burns, that means there's going to be some oxygen involved. So our products of burning are carbon dioxide and water. All right, 3 carbons on one side, 3 carbon dioxides on the other side. That means that we will have 6. Oh, nope, we can't have 6. Before we balance oxygens, let's balance the hydrogens. We've got 8 on the left. That means we've got 4 on the right. 4 H2Os. So now we've got our 3 carbons and our 8 hydrogens sorted. Now it's just about a matter of balancing the oxygens. We've got 4 on this side and we've got 6 on this side. So we need 10 all up. So 5 O2, because that'll add up to 10. This is a gas, this is a gas, this is a gas, and water is a liquid. Done. Good balancing. So let's actually get into some Stoke. So here we go. This is the reaction that we just wrote up in picture form. Woo! So this picture or equation is telling us about the mole ratio that's involved. So 1 propane plus 5 oxygens will give us 3 moles of carbon dioxide and 4 moles of water. So, same thing, so similar to our apple pie. If we had 1 mole of propane, we would get 3 CO2 and we would get 4 water. Now if we had 2 moles of propane, we have to double everything. So we'd have 6 CO2 and we would have 8 water. To produce 4 mole of water, which is already here, we would need 1 mole of propane and 5 oxygens. And to produce 10 mole of CO2, ooh, that's a bit tricky because we don't quite know the scaling, but we need 10 and we got 3, so we can divide. So that means we are going to have to times everything by 3.33. So you would need 3.33 moles of propane, and you'd need 5 times 3.33. Let me find that out. 16.6666 moles of oxygen. So if you don't know the scale factors, like say that's 10 to 10, you can just do 10 divided by 3 to find your scaling factor. So let's have a look at the Haber reaction. This is one of the most commonly used reactions in the world to get us ammonia, which is used in so many products. So the way that we do this is nitrogen always comes in 2s, hydrogen comes in 2s, and we land up with NH3. So in order to balance this out, let's look at the nitrogens first. We need 2 nitrogens, and that means we need 6 hydrogens. So if we just put a 3, balanced. Don't forget your states. So this is a mole ratio of 1 to 3 to 2. So the question is asking how much hydrogen is required to produce 5 moles of ammonia. All right, so we want 5 NH3. So what's the scale factor to go from 2 to 5? Well, you just go 5 divided by 2, 2.5. So we got to times everything by 2.5. So if we're looking for hydrogen, we'll times 3 by 2.5. And what do we get? 7.5. Easy. So there are these want got kind of things, but if you're just able to shift one reaction to the other, by finding the scale factor, you've done the exact same thing. Woo! So 7.5 moles of H2. Let's have a look at this one. How much H2 is needed to fully react with 4 moles of N2? All right, so if we got 4 moles, that means we're timesing everything by 4. So we're going to times this by 4. 12. Done. How good is this? So now we want 12 moles of H2. Woo! All right. Next up, I should write mole. Ooh, how much NH3 is produced from 0.72 moles of N2? I've written it down here to help us. So now we've got 0.72 N2. So we've times this by 0.72. So that means we have to times 2 by 0.72. And that lands up being 1.44 moles of NH3. So hopefully you're feeling a little bit more comfortable now with scaling between different reactions and using this as stoichiometry to find out how much chemical you need based on its equation. In the next video, we're going to go through a couple questions putting this all together.